Hello again. In this segment, I'm going to discuss a few things related to the mechanical behavior of the material before we get into its utilization in design. So what we will be talking about are things like cold work. How do we use cold work to strengthen the material? We will be discussing how we measure the hardness of the material, how we measure impact properties, and also we will learn about the qualitative aspects of properties as a function of temperature or strain rate. This type of information is useful for the designer to know because although it is not exactly quantitative, it will give you a good idea about how to select the material and how to utilize it. So the first segment is going to be on cold work, which is going to be quantitative, how we can determine the cold work, amount of cold work, and how that strengthens the material. And then I'll move on to more qualitative description of material properties on in the next part. So if you look at the idea of what we will be discussing, we will discuss number one, cold work. Then we will discuss the properties of hardness of the material, how to measure it, and how it is related to the yield and the strength of the material. We will discuss also impact properties. And we will discuss the dependence of the strength on both the temperature and the strain rate of the material of the in a particular design. And finally, I'm going to just indicate another type of test that is used to determine the behavior of the material called the creep test. So we will also outline that. So let's look at cold work. So in the cold work idea that you will see here, we will just look at cold work in the following way. Suppose that we have a material and the material is tested in tension. So you want to draw the stress-strain relationship. It's going to look like this. So the stress-strain relationship will be as you increase the load, you can express stress-strain relationship in a different way in which you plot on the vertical axis the applied load and the horizontal axis the change in the area of the material. So this is called a reduction in area deformation. So if we start with a pristine sample that looks like this, then it will deform and the area of the test section is going to be reduced. So the original area, let's call it A sub 0, and the area after deformation, we're going to call it A. So on this axis here, A, in fact, is a decreasing parameter. So A0 is the largest, then the area is decreased. AI prime is less than A0, AI is even less, and AF is the final area before fracture. So before fracture, the material, the volume of the material decreases in the middle section, and you get localization, and then the cross-sectional area becomes very small before the fracture, and this cross-sectional area here before fracture, we're going to call it A sub F, which is the area just at the moment that we have fracture. So another measure of ductility, we learn a measure of ductility, which is the change in length divided by the original length. But we don't know if that change in length is uniform over the entire sample or is localized. So we have to look at a different measure of ductility. And that measure of ductility is the degree by which the area decreases. So if we take the original area A0, subtract the final area, and divide it by the original, we get another measure that's called the reduction area. So the reduction area is similar to strain, but at failure, but it gives an indication about whether the deformation is localized and the fracture is a localized fracture. So the reduction area is given here, and you can express it as 1 minus AF divided by A0. Let's follow the load curve as a function of the area in here. You see that there's going to be a linear portion of the curve. This when the deformation is elastic until we get to a load that is called P sub y, which is the yield, the load at which you have yield. Beyond that, the material deforms plastically, so the relationship between the load and the area is now nonlinear. And if we get to a load P sub I, any particular load P sub I, and then release the load, we will recover the elastic part of the deformation. So the area that is recovered is not A0, but it is a little bit smaller than A0. We're going to call it AI prime. And on the same scale, if you go vertically down, the corresponding area is called AI. Generally, AI is very close to AI prime, so for simplicity, we will take the value of AI to be the same as AI prime. In other words, this is the area, whether you call it AI or AI prime, it is the area that has a permanent set. So the material has deformed, and now the cross-section has a permanent set and is reduced in that permanent set. In that case, we're going to say that the material has been work hardened at this point. So if we're going to load up again, we will continue, and the new yield point is going to be decided by this PI, not the PY, because the material now is a new starting area is AI prime, and then it will behave elastically up to a new yield point, and this new yield point is obviously larger than the original one, and therefore we have gained a certain amount of load carrying capability, and this load carrying capability is the work hardening that the material has undergone. So to kind of describe this work hardening idea, we're going to define a new factor that is the difference between the permanently set area that has resulted from the initial deformation and the very initial cross-section before the deformation, A0. So A0 minus AI, or AI prime, divided by A0 is a fraction, and this fraction we're going to call it W, the work hardening factor. So the work hardening factor here expresses the permanent set in the material, and therefore the cross-section, the permanent set cross-section, is equal to the initial cross-section times 1 minus the work hardening factor, as you can see here. So if I'm now applying a load on the work hardening material, the load is going to increase on this line until it comes to a point, and this point here is a new yield point. So this is new yield point that is larger than the original one, and therefore the material is stronger. However, the ultimate strength is the ultimate load is the same, P ultimate is the same, and the deformation will go on this route. So we ask ourselves if the ultimate load is the same, but the area has reduced. What is now the new ultimate strength of the material? It's basically load conservation. The load is equal to the area times the new ultimate strength of the material. We can also figure out how to compute the new value of the yield strength of the material. So in order for us to do that, we're going to do a little bit of math, and that's what I'll describe here. So if we consider now that any material can be described by a relationship between the stress and the strain in this fashion, sigma is equal to sigma 0 epsilon to the power m. This is called the Ramberg-Osgood relationship. And in this relationship, it is usually applied to the true stress and true strain, and m is called the strain hardening exponent. So this is a strain hardening exponent. And it's usually on the order of 0.2 to 0.3 for some of the steels. So if we apply that, we want to substitute. This is the true strain, and the true strain is epsilon. The true strain is equal to the natural log of L over L0, and now I want to convert this to areas. So it is from volume conservation, it will be a natural log of A0 divided by A. And if I want to find now if I want to apply this relationship exactly at the new yield point, I need to know this factor here, and this factor is called the strength coefficient. So this is strength coefficient. So every material, every metal, steel for example, has two numbers, the sigma 0 and the m. Once you know those, then you would know the relationship between the stress and the strain, true stress and the true strain, and we could use it to determine the realized strength of the material as a result of cold work. So assume that we have these two numbers, the strength coefficient and the strain hardening exponent. Let's now measure the change in area. We found the new area after the deformation, put it into the strain expression to find the true strain, use the true strain to find the new stress of the material that can result in yielding, which is the new yield point. And that's the procedure I'm going to follow. So we will first write down the S yield prime. This is the new hardened yield strength. This will be equal to sigma 0 times epsilon I to the power m, and epsilon I is now determined as the true strain exactly at that point. So at the point at which we released the load. So it would be ln of A over A0. We figured it's L over L0, which is A0 divided by A. So I can write this sigma 0 ln A0 divided by A, and A at this point is A sub I, exactly at this point I. So I can write it ln of 1 over 1 minus W, because we know that A0 AI is equal to A0 times 1 minus W. We have concluded that this is from the definition of the work hardening factor. So that is an expression that I can use now to compute the new yield strength as a result of cold work. And we're done with that. Now, the other strength measure that I usually like to find is S ultimate prime. So this is also a new ultimate strength of the material. From the fact that the ultimate load is constant, is the same, then we will apply the load to be equal to the strength times the cross-sectional area before and after. So we know that now P ultimate is equal to the cross-sectional area times the ultimate strength. This is before we did the cold work. After we did the cold work is equal to AI times S ultimate prime, and AI is less than A0. So again, I can find an expression for S ultimate prime as equal to S ultimate times A0 divided by A. And using now the cold work factor, that would be S ultimate divided by 1 minus W. So I have now another expression that I can use to determine the new value of the ultimate strength of the material. So I have expression 1 for the yield, expression 2 for the ultimate strength of the material. So let's now take an example, and this example here will illustrate how we use these two expressions in determining the influence of the cold work on the yield strength and the ultimate strength of the material. So example, let's read it together, is that we have an annealed IC 1018 steel, and this steel has we have it, the properties are in table A22. It has a yield strength of 32 kpsi and an ultimate strength of 49.5 kpsi, and a fracture, stress at which you have fracture, true stress at which you have fracture is 91.1, and then you will have the two parameters that I was describing. The strength coefficient is 90, and the strain hardening exponent is a quarter, and the strain at fracture is 1.05, means 105%. So we want to find the new value of the strength of the material is given a 15% cold work. So 15% cold work, it means that we have now determined that W is equal to 0.15. So A0 over AI is 1 over 1 minus W. We find that the ratio of the original area to the new area after imposing the cold work condition is like 1.176, meaning that I have 17.6% reduction in the area. So having computed that factor, then I can use the previous two formulas. First, I calculate the true strain using ln of 1 over 1 minus W, and that gives me 0.1625, and put it into the Ramberg-Osgood relationship, get 557.1 kpsi, and use the conservation of force before and after at the ultimate point to get 58.2 kpsi. So that's a pretty good example that showed us the idea of how to design a material for a particular level of strain, for a particular level of yield, and also the ultimate. Obviously, we cannot do that arbitrarily. We cannot increase the yield on the ultimate to a very large amount. Otherwise, the material will fracture before we actually utilize it. So it has to be done within a certain range of cold work that is appropriate for a particular alloy that is used in the design. Now I'm going to switch to talk about a few qualitative aspects. We said that we will discuss what is the hardness of the material, how can you measure it, and how can you relate it to give you information on the strength. Second, we wanted to also discuss the impact properties and also the dependence of these properties on temperature and strain rate. So we'll go through that together one by one and try to understand it here. So the hardness is defined as the resistance of the material to penetration by a pointed tool. And therefore, we can use a pointed tool either in the form of a pyramid indenter or a spherical indenter. And there are two common hardness measuring systems, and those are the Rockwell scale and the Brinell hardness number. So Rockwell, it has 3 scales, A, B, and C, and they specify the indenters and the loads for each one of these scales, and the hardness numbers are relative. If we use the Brinell type scale, this is called H sub B, so this is H sub C, H sub R, Rockwell. This is H sub B for Brinell, and the load is divided by the spherical surface area of the indenter. So in the case of the Brinell hardness test, then H sub B is equal to P divided by the surface area of the sphere. So it's 4 pi times R squared. So you have a sphere, and the sphere is indented into the material. This is the material here with a force P, and therefore, since it is the ratio of the force divided by the area, then the units of the Brinell hardness number are going to be in the same units of the stress. So you can have it either in megapascal or in KSI. It turned out to be that there's a very simple correlation, practical correlation between the Brinell hardness number and the strength of the material. Strength means ultimate strength. So that can be very useful because we could use this relationship to just push in the material, get a Brinell number, so maybe a little device, you just push it on the material and you get a Brinell number, and then boom, we can get the value of the tensile strength, ultimate, and the yield for that matter from simple correlations. This is extremely useful as we use materials in practice. The materials age and their properties change, and it will be useful to do a non-destructive test of that nature. So here it goes, like we can just look at the relationship that for the case for steels, for example, then you have the ultimate is say half of Brinell if you're talking about kPSI. So if you have the Brinell number is 200 kPSI, then the ultimate strength will be 100 kPSI. Very simple. For cast iron, the ultimate is equal to 0.23 of the Brinell minus 12.5. So these are kind of practical correlations that have been developed over the years, and they use in the steel industry. Let's see a practical application of this method. Suppose that you are in a foundry and produce many steel rods from the same lot. So we know that there are going to be variations from lot to lot, but even within the same lot, the strength properties can have kind of a distribution in them. And you want, as an engineer, to determine if the strength levels are within the specified range so that people can use them outside in design. So it's a qualification type test using Brinell. So basically what you want to do is use Brinell over the lot, and then from these numbers you can get the statistical distribution of the strength. And here is the example that we will show. So we're saying that it is necessary to ensure that a certain part supply of a foundry always meets or exceeds ASTM number 20 spec for cast iron. And therefore, we want to know what hardness should be specified. In other words, it's a kind of a backward problem. We want to you want to have an ASTM standard number 20, which means that the grade 20 steel should have a minimum of 20 kpsi. That's kind of the ASTM standard number 20. So in order for us to assure that this within a certain 20 points on the hardness test, we use the relationship that we discussed before. If you remember before here, this is the relationship. So if you write it backwards, like HB will be equal to S ultimate plus 12.5 divided by 0.25. So if you do that, then you find that HB that corresponds to 20 kpsi is 141. So as an engineer, you can tell that the foundry that every one of these rods have to be tested with Brinell tester, and the Brinell tester, if you accept a spread of 20 points, it should have a hardness Brinell hardness number between 145 and 165. So that's kind of a good example that we will apply to the hardness. The next property that I'll talk about is impact. In many materials, as we define resilience and we defined toughness, we need to have a measure for the energy absorbed. If we're doing a stress strain type curve, the strain rate is usually very slow. So we get resilience and toughness out of the stress strain. However, in other applications, for example, crash applications in automotive industry, we would like to know the amount of energy that is absorbed before fracture of the material in high strain rate impact type tests. So to do that, we utilize something called a Charpy test, and that is going to give us, we take a piece of material and push on it by a pendulum. Pendulum will fall on it very fast, and it will break it into two pieces at a certain height, so we can determine the amount of energy absorbed, and from that we can decide if that is enough for a given crash impact test. However, this impact energy for fracture is actually a very strong function of temperature, especially for steels. So that's what I will describe here. So the energy, we use a notch bar test to determine the brittleness of the material, and in the notch bar test, it is we take a bar like this and notch it from the bottom, and then we support it on simple supports. So we have a simple support here, a simple support here, and then we would like to use a pendulum, and the pendulum will let's say be at this point here. It starts the fulcrum at that point, and then you have an arm, and the arm of the pendulum is here, and then you have some impact anvil that is like this, that has a sharp edge like that, and then you swing the pendulum until it hits the material, and from the height that away from the surface h, you have an energy that is equivalent to the potential energy of the material mgh in foot-pound, and that will be a measure of the energy absorbed before fracture. So you just induce fracture. Once the material fractures, then you can have this energy absorbed as the Charpy test. So this Charpy is one of the inventors of this test. So if you do this test at different temperatures and plot the energy absorbed at fracture versus the temperature, you'll discover something very interesting. You'll discover that at low temperature, that energy is very small. So the material or the steel can be very brittle. So it can behave like glass at very low temperatures. So if we're using steel pipes that have low impact energy in the Arctic region, for example, they would have very low fracture toughness or fracture properties, and we better be careful in utilizing the steel. So we have to have another type of steel that has higher absorption capabilities for the energy. So let's look at the the plot here. So you will have the Charpy energy absorbed, MGH, in foot-pound, 20, 40, 60 for a standard specimen, ASTM specimen. And they plotted as a function of temperature in degrees Fahrenheit. And then you see that there is an increase, the very low values at low temperatures. And then as the temperature increases, then the value will increase. And you have a transition temperature, could be below zero or about zero. And that transition temperature is defined when the Charpy energy is like 30 foot-pound by definition. And that gives you a definition of the ductile to brittle transition temperature, or in short, DBTT. So every material will have a DBTT, and the lower the DBTT, the better it is in design applications, because it will have generally higher impact properties at operating temperatures. And that's kind of what we look for in crash or impact applications, right? Now, the next property that I'd like to discuss is how does the strength depend on temperature? And how does it depend on strain rate? Well, obviously, as the temperature increases, the yield strength is expected, material is expected to be softer. So the strength is going to be less, and the ultimate strength is going to be also smaller, both the yield and the ultimate. So that's what we expect. Now, if I look at the effects of strain rate on the yield strength of the material and the ultimate strength, I would expect that the material kind of stiffens as you hit it harder. So the harder it is, the higher the strain rate, the more the material is going to resist. And that's basically the qualitative aspect that we're looking after right here. So if you look at the effect of strain rate on impact, then you see that the ultimate strength increases and the yield strength also increases. And on the contrary, the elongation kind of saturates in here. So both the ultimate and the yield increase as a function of the strain rate. So this is like tensile here, tensile test. And this is impact right here at this kind of strain rate at 10 to the 3, 10 to the 4, it will be an impact test. And you will see that the ratio of the yield to the ultimate becomes higher and higher, so the yield kind of reaches closer to the ultimate. The ultimate doesn't increase as much as the yield strength, and the yield strength kind of catches up with the ultimate. You can see it's trying to catch up with the ultimate at higher strain rates. Let's look next to the dependence of the strength on the temperature, and we see that the material softens. So it softens like this. This yield is, decreases as a function of temperature. This is room temperature here. And the ultimate increases slightly, and then it decreases again as a function of temperature. So both they decrease. This is the ratio of the strength at temperature divided by the ratio of the strength at room temperature. So ST is any one of them, either yield or ultimate, at temperature, and SRT is the same strength but measured at room temperature. So With that, we have one more property to discuss, and that is the creep test before we close this segment. So in a creep test, we have a bar, and the bar we apply a load, but we apply the load at very small strain rate. So epsilon dot is very small, like on the order of 10 to the minus 6 second minus 1, for example. So in this case, the material deforms as a function of time. So if I measure the deformation, which is delta L over L, as a function of time, then I find that the material actually will increase the creep. You get a little elastic part, and then it will increase very rapidly the deformation, and then it will go into a sort of kind of a continuously increasing linear phase, and then it will accelerate until you have fracture here at the end. So we divide the creep strain. So this is strain epsilon as into 3 regimes. One regime here is an initial first stage creep, which is transient creep sometimes is called. Second stage is called the steady state creep, and third stage is the creep rupture stage. So at this point here we have creep rupture. And in most of the designs that we know of, most of the material spends most of its time in the second stage. That represents the majority of the time spent by the material during its lifetime. So in a creep application, like in pipings, for example, in power plants, the piping systems can last for 30 to 40 years, very long time. If you measure the strain as a function of time, you find that initially for maybe a few weeks, you get some kind of acceleration of the strain, and that is the transient phase. And then it will start kind of creeping at the same rate for maybe 20, 30 years, very, very long time. And then in the last maybe year or so, or less than that, it can just go into this tertiary creep stage, because the grain boundaries start to kind of get loose from each other, and you get cavitation on the grain boundaries, and you start getting into the fracture regime. So we're going to stop here, and we will continue next segment.